Welcome to this presentation about decision trees. Decision trees can be extraordinarily useful for analyzing data and even making predictions for the future based on data. They're very powerful, but they're sometimes intimidating for people that are just learning. We'll try to make this understandable and useful and have good examples so that decision trees can be part of your toolbox. Here are some basic notions about decision trees. First, it's a supervised type of analysis where we're trying to predict the value of a categorical or a class variable. We can use categorical data, nominal or ordinal, or continuous data, either interval or ratio, as predictor variables. We can predict binomial outcome as well as multinomial outcomes. And we make no distributional assumptions. It's a non-parametric test. Because of this, we are going to need more data than if it were a parametric procedure, such as linear or logistic regression. So what are the types of business questions that can be answered? For a given case, can we predict the value of a class variable based on the value of other variables? For example, is an individual likely to buy or not buy our product? Will a given individual respond or not respond to an advertisement? Is a credit application fraudulent or not fraudulent? And the list is long, and people use decision trees in these types of business questions all the time. Decision trees are used to work with basic classification problems. And a classification problem is how can we build a model to classify or predict based on known independent variables. And in this case, the independent variables would be age or balance. And then the data point lands somewhere in this grid. And the decision tree approach then seeks to split the data by the horizontal and vertical decision boundaries that partition the instances into regions of similarity. So here we get quadrants, and they're not equal in size, but this one is balance less than 50 and age greater than equal to 50. This is balance less than 50, age less than 50. This is balance greater than equal to 50 and age greater than 45. And this is balance greater than or equal to 50 and age less than 45. So we might segment the data so that we can analyze the quadrants and maybe get much more precision in our answers. Here are some terms that are very common when you work with decision trees. The first is entropy, and we did a video on entropy, and we did a lot of SQL calculations working with entropy. It is the amount of surprise or uncertainty or a level of information in a data set. Another measure of so-called impurity is the Gini impurity, and it's the measurement of the likelihood of incorrectly classifying a new occurrence of a random variable if that occurrence were classified according to labels that we're trying in our decision tree. Another measure in the same vein as entropy and the Gini impurity is classification error. And it's the fraction of training observations in a region that do not belong to the most common class. And so that's 1 minus the largest probability, and that's the classification error. Information gain is the flip side. Entropy characterizes the impurity of an arbitrary collection of examples. Information gain is the expected reduction in entropy that's caused by partitioning the examples based on a given attribute. The reason that they're often called decision trees is we create this structure right here when we're building decision trees. So let's look at the components here. This first one is known as a root node. It's the very top. So the first question that's asked is, the person, are they employed? If it's yes, we will not write it off. If it's no, then we'll look at this next node, and these two are interior nodes. So we look at the balance. If it's less than 50K, we will not write it off. If it's greater than or equal to 50K, let's look at the next node, and that's age. If the age is less than 45, we don't write it off. If it's greater than or equal to 45, we write off. And these two bottom ones are called leaf nodes. So decision trees are a data mining methodology where leaves and nodes are generated to construct a predictive tree so that the data miner can see the attributes which are most predictive of each possible outcome of the target attribute. For the rest of this presentation, we will make use of this iris dataset. Now, an iris is a beautiful flower. This example here is blue in color. The iris dataset is a small dataset from 1936 which is used frequently for creating machine learning algorithms and visualizations such as scatter plots. Each row of the table represents an iris flower, including the species and the dimensions of its botanical parts. And these parts include the sepal and the petal measured in centimeters. So here is a picture, and the sepal is this larger part of the flower here. These smaller portions are the petals. Here is what the iris dataset looks like in the SQL table. The attributes that we have are sepal length and width, petal length and width, the actual species of the plant, and we've included a species ID. So what ends up happening is we have the length, the sepal width, the petal length, and the petal width, and based on those, we're going to see if we can predict the species using a decision tree. The decision tree that we built will look like this. If the petal width is less than or equal to 0.6 centimeters, we already know it's of the species Iris setosa, and there are 50 of the 150 that are of that species. If the petal width is greater than 0.6, then we need to keep going down this next node. This is the root node. Again, this is the interior node. If the petal width is less than or equal to 1.7, we're at another root node. However, if it's greater than 1.7, we already know that it's an Iris virginica. So coming over here to the petal length and traversing down, if it's less than or equal to 4.9, we know it's an Iris versicolor, 48 of those. If the petal length is greater than 4.9 centimeters, then we go to the next interior node. If the petal width is less than or equal to 1.5 centimeters, it's Iris virginica. And if the petal width is greater than 1.5, then it's Iris versicolor. So that can be pretty complicated when you have a large tree with several nodes, but we can build techniques to start to train our data to see how well the decision tree we built works out. We will create two tables to do this decision tree in SQL Server. The first table holds the actual iris data itself, and we have our sepal length, sepal width, petal length, petal width, and species right here. One note is that because we did dot notation here, we have to enclose those attributes in a double quote. Also, the primary key is going to be the species ID, and it is called type identity, and that is built automatically and it increments automatically. The second table is going to hold our training model. So it is called iris models. And the first attribute is the name of the model, and it's varchar 50. And the second one is var binary max. So if you try to look at it, it looks like hexadecimal because it's an object. Once we've built both of the tables, it's time to download the iris dataset. And there are many locations for that, but here at UC Irvine is where I downloaded the iris dataset. And I went to this folder, you download it, and notice that there are 150 rows in this dataset. Once I downloaded it, imported it into SQL Server, and I gave it the same data types as we saw in the DDL for the irises data table, this is what it looks like. So we have the ID, the sepal length, the sepal width, petal length, petal width, the species, and the species ID. And here we do a select count star, and we see that we have 150 rows of data. Here is the stored procedure to build our training model, and it is a mixture of SQL and Python. So here we create the stored procedure, and it is going to create an object, so we won't be able to view it directly in the table, and that's of type var binary. Here's where we specify that we're using Python and we're executing the external script. We're importing pickle, and I'll talk about that in just a moment. And we're also going to use the Gaussian naive Bayes for the distribution. Here we get a pickle dump of the data, and the data is the sepal length, width, petal length, petal width from iris data, and here is getting the iris data from SQL Server. So we put it into the parameter that XP execute external script wants, and that's this parameter at input data 1. So pickling is a way to convert a Python object into a character string. And a Gaussian naive Bayes algorithm is a special type of naive Bayes algorithms. It's used when the features have continuous values and all the features are following a normal distribution. Here is our stored procedure to create and train decision tree models. First, we declare a variable to be of an object data type, and specifically var binary. Then we declare a second variable that will hold the model's name. We're setting this one equal to naive Bayes. We execute the stored procedure that we built in the previous slide, and we are having output from that stored procedure. We are going to get rid of any old rows that we ran in our models table. Then we insert into the models this new one that's created by executing the stored procedure. Once we've executed the last code on our last slide, we can do a select star from iris models, and this is our output. The model name is naive Bayes, and this is that hexadecimal object output that we have stored here in this table. Once we've built the training model, then we apply that training model to a majority of our data. Now, a rule of thumb is use 20% of the data to train your model, and then use 80% of your data against the model that was created by your training data. So here's our stored procedure. Here is where our previous model that we had in the previous stored procedure, that's where it's loaded. And here we have our output. That's a part of the difference of this stored procedure as well. When we execute that stored procedure, this is our output. We have the actual species ID here, the predicted species ID here, And right here is one of the times where the actual and the predicted was not the same. So that means our model is really actually pretty darn good, but it does miss every once in a while. So let's execute the stored procedure that will take the training data and apply it against our main base of data to see how well it does with prediction. We execute this stored procedure, and frequently it takes a little bit of time to run. And so it has to go make those predictions and run it against the model. Here is that one instance that I referred to earlier, where we had the species ID here of a 1 and the predicted was a 2. So we were able to execute our stored procedures, which had a substantial amount of Python in it. And the Python is the part of the program that's doing the decision tree and making the predictions. Now that we've imported our data into SQL Server and we've made a decision tree and we've analyzed it, it's really good to use other applications as well. And so we're going to use Tableau to visualize data. Now there are a lot of ways that you can get the data. You can get it from an Excel file, a text file, JSON. I like to show how to get it from a server. So if this was at a remote server, I would type in either the URL or the IP address. Then I would authenticate and I would sign in. Now the data is not sitting on this server, so we will connect to the local instance of SQL Server. So let's get it off of the local server, and I could get my local server and paste the name of that instance here. At this point I am using Windows authentication, so I just click sign in, and now I am connected to SQL Server on my local computer here, and I'll choose the database. The one I'm working with is called Iris SQL. So I clicked on that, and now I've got the data imported. So let's build our first graphic here. We'll double click on the Iris data, that's what we'll use. And I'll scroll this down a little so we can see it. I'll update now, and now my data comes in to Tableau. So I go to my sheet, which is where I will make my graphic. Now I'll put my petal width, here's a column, and I need to change this to a dimension. And I'll put my petal length here as row, and I will make that also a dimension. Now I'll drag species into the color here so that we can see these by species. Now if I can squish this over a little, maybe we can see the species right here up in this right hand corner. So the blue ones here at the bottom part of our graph are Setosa, and the yellowish orange ones here, they're versicolor, and these red ones are virginicas. So we make our graph here, we can edit the title, and maybe we will call this Iris Graph. And I might take those off because we don't need them. And apply. So we can do more edits, but this is our first graph. Our x-axis there at the bottom then is petal width. See if I can bring this down to show it. So down here at the bottom is petal width. Petal length is here. And we see color coding of each of our iris data points. Here we are going to make another graphic in Tableau, and this one will be a histogram that is a comparison of each of the species between petal length, petal width, sepal length, and sepal width. So let's get started. And we're going to put species up here in columns. And then we're going to put petal length in rows, sepal length, sepal width, and petal width. So we're getting that started. And we don't want to do a sum here. We just want to see the attribute. So we'll change it to a dimension for each of the 4 here. Let's open up the marks so that the changes we make are made effective to all 4 of the windows. And let's start dragging our measures here and drop them on tooltip, and notice that we have the aggregate sum length there. So we'll go petal length, sepal length, sepal width, and petal width. Now let's drop species onto color so that we can see a different color for each of the windows. And it's looking pretty good here. So let's make this the bar chart that we wanted, and that's just exactly what we want right now. Let's change our title and bring the legend over here to the left side. So to work with the title, we'll double click it, get rid of the default, put in our title. Let's dress it up just a little bit. Maybe I'll change this to semi-bold. Maybe I'll make it a little larger. Oh, let's add some color right here. And maybe we'll center it. Okay, I like that. Let's drag and drop this legend over here and put it in our left window. And this is a very basic diagram, but we see here petal width, sepal length, petal length in a bar chart, and we see those measures in a bar chart or histogram. Now that we've built those 2 graphs, let's build a third, and this one's going to show the difference between the predicted species by our model and the actual species. So to do that, we'll go down to our data source here in the left-hand part of the screen, and we'll go up to the top left here and go to New Data Source. We're going to change it from a table to a stored procedure. Let's go to SQL Server, let's sign in, and choose our database, which is Iris SQL. Now, as I mentioned, we could do a table, but that doesn't have the data that we want. Let's run the predict species stored procedure. Now I have to pass it the value, and that's the naive Bayes, and I click OK. And now I'm going to update to bring the data in so that I can use it in my graphic. Let's open up a new sheet, and here are our measures. Let's put ID up here on the top shelf, and let's put species predicted here. Now we're going to change this one to discrete and a dimension. Let's change this one to continuous and dimension. Let's come over here and go to species ID and drop it on color. Let's change our rows to discrete. Let's change our title and dress it up a bit. So we double click on the title, and let's get that here, and let's change it from Tableau light to maybe Tableau semi-bold. Change the color. I don't know, maybe this blue version looks really nice, and let's go larger, and we'll apply that, and I kind of like that. Let's go ahead and center that then, and we've got a nice title. So let's drop the show me and bring this over to here. That's our legend. Let's go ahead and edit our legend title here. We'll click here, edit title, and I'll take out the sum, and I'll change that to have a species and an ID space. That's a small thing, but it's tidying up, and you see that that's changed over here. Now this is a really basic graphic, but notice this first species of irises, the predicted and the actual is all the same. This second set of irises, there are 1, 2, 3 where the predicted versus the actual is different, and here 1, 2, 3. So that turns out to be a very good predictor here of which species you're looking at, given that you didn't know beforehand. So this is a good exercise in seeing how decision trees work and to make predictions. To conclude this presentation on decision trees, we note that we acquired the iris data, structured the data, and got it ready in an SQL database. We gave a comprehensive treatment of the iris data set, which is an ideal data set to illustrate decision trees. We built a training model, and after we applied our training data to the training model, we ran the model against the rest of our data set to see how good it was at predicting outcomes. Then we built 3 different Tableau charts using the iris data to illustrate the next step of visualizing data and outcomes.